This is the simple measurement which displays amplitude and phase on speed frequency. This is the setting. And this is the result screen. This measurement displays the amplitude and phase relations between two sensors, which are mounted on two different planes. The relations are measured just on one frequency. Usually it is speed frequency, but you can manually enter any other frequency. This is the result screen. You can see the phase difference between B and A sensor on frequency 15 Hz and the amplitude ratio between B to A and the coherence value. The coherence value should be near 1. If it is low, then vibrations on selected frequency are not stable. The averaging must be used to get coherence value. The coherence is always 1 when averaging is off. The order analysis displays values of amplitude and phase on speed frequency and its harmonics and subharmonic multiplies. Select the orders measurement and define the harmonics and subharmonic parts you want to measure. Now you can see all orders, amplitudes and phases. It is standard spectrum, but the X is labeled in orders. We set the number of orders, it means the X range. We set also the maximum frequency band Fmax. It is the security option. If we set only the number of orders, then we can wait very long time for results in some situations. This is the example. When we use two proximity sensors, then we can display the position of shaft in bearing. This is 0 machine speed, less than 100 RPM usually. Shaft is assumed to be at the bottom. Normal positions on nominal speed. The position corresponds the direction of rotation. The position tells nothing about vibrations. It is just the DC part of signal. The center line is the measurement of shaft position during run-up. We use the run-up module in the analyzer. We need to set the trigger properties. The run-up measurement is the series of individual readings. Each reading must be triggered. For turbine analysis, we usually use the triggering by speed and time. You can see the half Hertz value for the speed change. It means that when actual speed changed more than half Hertz compared with speed of last measurement, then new measurement is taken. You can see 1 second value for the time change. It means that when the actual time is higher more than 1 second compared with last measurement time, then new measurement is taken. The sensor's properties is set already in sensors menu item. We only need to define the center line measurement, and now we can run the measurement. We can download the measurement to DDS software, where we can define the available clearance. And this is the graph. This is the setting of clearance. This is setting of 0 position. The orbit is the measurement of the shaft vibration around its position in bearing. We need to define A and B sensors. Be careful to set it correctly according to the direction of rotation. We can see here the red circle. It is the orbit. It displays the circular motion of shaft center. This is the result screen. The black arrows are the direction of rotation. The orange arrow is the direction of the shaft vibration. It means the direction of orbit development. The short orange lines displays the key phaser position. Now you certainly would ask me why the key phaser are not in the same place. It is because of the data. It is the run-up record. That is why the positions are shorter and shorter. You can see the shaft position is 0 microns on both axes. We do not use the DC channels, just only the AC channels. It means that DC part was removed. Now we set the DC channels. It is in sensor setting. We set the DC channel 1 for AC channel 1 and DC channel 2 for AC channel 2. You can see that the center of the circular motion is not in 0 position. This is a very special function of our analyzers to display both information in one screen. We have been talking about direct measurement of orbit, but there is another similar measurement which is called filtered orbit. This measurement works with order analysis and then the orbit is mathematically developed. What is the difference? We can select some orders and only these orders will be included to orbit. The measurement setup is the same as for orders measurement. This is the initial screen with orders. We can see that only first 3 orders have higher amplitudes. This is the filtered orbit only on the speed frequency. You can see that all other harmonics are switched off. Only second harmonic orbit is on this picture. Orbit in this picture contains first 2 harmonics. Orbit in this picture contains first 3 harmonics. Let's begin with simple example. We have been talking about filtered orbit. I have a question. What shapes the orbit can have on only one frequency? For example, the speed frequency. Generally speaking, it is the ellipse shape. On extreme case of the ellipse, it is exact circle. The second extreme is the line. Let's talk about ellipse. Imagine that the shaft vibrates on 2 exact circular motions. One motion is in rotation direction and has 1 amplitude. The second motion goes against rotation direction and has the second amplitude. This is the first motion in rotation direction. This is the second motion in opposite direction. What happens if I run both motions together? It is surprise. The ellipse motion shape is the result. Now please imagine the spectrum graph. It is a little special because it contains the positive frequencies and negative frequencies. The amplitude of motion in rotation direction we draw to positive part. The amplitude of opposite motion we draw to negative part. This spectrum is called full spectrum. Splitting of amplitudes to positive and negative frequencies contains next information for analysis. Now we show you the example measured on analyzer. We select the order spectrum measurement and we set the full spectrum parameter to on. This parameter is also available in standard spectrum measurement. On the top is direct orbit measurement. In the middle is full spectrum amplitudes, and in the bottom is full spectrum phases. We see just 2 higher amplitudes on speed frequency. Now we enter these values to the simulation program. You can see that motion shape is the same as orbit shape. Now we will show the extreme cases. If the full spectrum has amplitude just on one side, then the orbit shape is exact circle. If the full spectrum has the same amplitudes on both sides, then the orbit shape is exact straight line. I hope that these videos help you to understand all ADAS analyzer's features, which are designed for turbine vibrations analysis. Thank you for watching.